Hey there, and welcome to another mini VMware Secrets Manager demo. In this quick demo, we are going to show how we can end-to-end encrypt secrets from the browser to the server so that when we are transmitting something sensitive, we can have an additional layer of encryption on top of TLS. So why would we need it? So wouldn't HTTPS secure enough because it's does security encryption over the wire. So if we have a trusted trusted root authority, wouldn't that encryption be enough to dispatch the data that we are sending securely? Well, depending on the standards that we are going to align, the answer is mixed essentially. So for example, mostly HTTPS TLS is generally considered sufficient for encrypting data in transit. However, when handling what's considered or what's categorized as highly sensitive information like credit card data or like a root key of a master database or like some important secret that when it is shared, it will allow an adversary to ripple and attack to multiple places essentially. Those kind of highly sensitive information is recommended to be recommended to use a stronger encryption even in transit, and that encryption is recommended or depending on the standard can even be strongly encouraged or even mandated to be end-to-end at the application level. So even the HTTPS TLS is compromised, the data in transit will still be protected by a second level of wrapped encryption. For example, PCI DSS goes beyond TLS and recommends encrypting cardholder data at the application level end-to-end. Similarly, GDPR or HIPAA, the health-related standards, require application-level end-to-end encryption while passing secrets or sensitive data in transit. So as a summary, while HTTPS TLS encryption meets many basic requirements, when we are passing secrets around, an additional level of caution would be useful and would even be important when you want to align with certain regulations and standards for your application. So in this demo, I am going to show it, and I will first dive into a mini sequence diagram to explain, how this interaction is going to work. So we have the end user, and the end user will enter details in a UI, and the UI is this one that you see here essentially. Because this is just a proof of concept, we don't have any buttons or text boxes or anything, but you can think of this as a JSON representation of whatever the user enters in the UI. So when the user clicks this encrypt and send button, several things will happen. First, there will be a key exchange between the browser and the server. The key generation part on the browser will be done by web cryptography APIs, as I said, and the key creation and generation and exchange on the server will be done by Go standard cryptography APIs, essentially. So what the client will do is, let me zoom here a little. The client will create a key pair. Actually, it will create two key pairs, but for the sake of simplicity, I'll just assume it as a single key pair. Yeah, but the client will create a key pair for encryption and another key pair for signature validation. That makes it, that is better separation of concerns and also better security. But for the sake of this argument, I'll just assume that client has a single key pair, and I'll also share the source code so you can investigate and observe what's happening at your own convenience with more detail, essentially. So client creates a public key, private key, an N-once. N-once is a kind of a text that is transmitted only once, and it will sign that nonce and send the public key nonce and the signature to the server, and server will verify the signature of nonce based on client's public key. And if the signature is verified, the server will get the client's public key. It will create an AES cipher to encrypt larger blobs of text, and it will also create a private public key on by itself as well. And then it will sign the payload that it's going to send to the client with its private key. It will encrypt the AES key with client's public key and sends the payload back to the client. So what client does is then it will verify the signature of the server. And in that exchange, server also sends its public key for the verification purposes. So client verifies the signature of the server, and then it decrypts the server's AES key and saves it in memory, so that when an encrypted data comes from the server, it would be able to decrypt it. So then the client, let me go back here. The client will encrypt this payload with server's AES key, and it will create a separate signature. This is server, by the way. Let me fix it. Let me zoom. Okay. So it encrypts this JSON payload, and it encrypts the JSON payload with server's AES key. It creates a signature using its private key, and since the client's public key has been sent in the former interaction, the server can verify the signature of the client's payload by using client's public key, and server can decrypt the payload because the client has encrypted the payload with the server's AES key. The cool thing about this interaction is in this boundary, like let's say this is the network boundary between client and server, nothing sensitive is exchanged in plain text. So we are sending public keys. It is public, so it can be passed in public. But other than that, private keys, AES keys that are used for encryption, and the private data, the secrets data, are all passed encrypted. So that means you see that this is plain HTTP, but although it is plain HTTP, when you send it, the data it will be like this. The data that is transmitted will be encrypted, garbled. So even somebody tries to intercept it, they won't be able to. And add TLS or MTLS on top of this, and the interaction will be rock solid and compliant with many standards, essentially many regulations. So I'll refresh this one, and also let me see what I can show. I won't go into the Go code too much because I wrote it in a hassle. I'll just slowly, scroll it for the sake of, completeness. But I'll share the source code. It's in VMware Secrets Manager's GitHub repository. I add it here as a comment as well. https github.com VMware come on Tanzu /secrets manager. So it's right now in a feature branch. I'll push it after this recording, so you can be able to see it in your own spare time. But regardless, this is the code. It's doing whatever the high level sequence diagram explains. And there are lots of comments. I'll clean it up. That's why I'm just shying away from going through the server code. It is working, but it is not in its best shape, but it does its job essentially. The JavaScript is a little bit more organized, so I can just go through it. We have two buttons, one encrypt button and one decrypt button, as you see in this UI. So when the user presses on the encrypt button, first we do a handshake to verify the server's authenticity. What I mean by that is we create a bunch of encryption keys on the client end. We send it to the server. We verify server signature. And if the server signature is invalid, we like bail out. We don't do anything else. And if the server signature is valid, then we extract the AES key that the server has sent to us in the first interaction. We save that AES key and we do any further encryption operation using server's key, essentially. And the next thing that we do is encrypt that payload that you see on here, this JSON payload, and send it to server. Normally, like this should be a separate step. This is here changed just for the sake of convenience. So it normally, like in a normally useful workflow, the user will likely enter a bunch of boxes, drop downs, text areas, and fill a form, and then press submit, and then it will go. It won't be in a single step, just encrypt, handshake, and send. But it's still like this is splittable. For the sake of demo, it is combined. But you'll see that even at this stage it will store and retrieve. It is able to store and retrieve the data accordingly. So it encrypts and sends the encrypted data to the server. The server stores that data, and when the client requests it, the server is able to retrieve the data. And the decryption is totally happening on the client side. The reason is because we have acquired server's AES key and server's public key. So we don't even need server's public key, to be honest, maybe for signature verification, but for nothing other than that. So we have whatever we need. So when we get an encrypted data from the server, we can decrypt it with the AES key that we received and decrypted already. So this is on the client, on the browser itself. Nothing on this decryption logic is going outside the browser. I'll show the network tab when I do the demo part, so you can see that no network interaction is happening on the browser as well. But that's that part. Other than that, I'll again expand the code somewhat, and you can look into it. But it is all to be fair, it's cryptography, so it's lots of keys and signatures and whatnot, and going through it will require you to read it, essentially. So there is key pair creation, there is boxing, unboxing, those kind of stuff. But like I said, this is open source, and I'll push the code out into the GitHub repository so you can consume and read it in your own time. In additionally, there is not here, sorry. Here there's course headers that I'm passing through because I am doing a one domain to another domain and port kind of an interaction. If this happens on the same internet gateway or on the same side, on the same domain without any port or domain change, then you won't need those host headers. But if required, the code also contains some course setup as well, cross-origin resource sharing, and that's that one. So let me, I have my servers open. Let me close this one too. The client one is, where am I? The server on the client is just a plain HTTP server. So I'll just what I do is I just run HTTP server, and it runs a static HTTP server on the client, and the server, the Go server, is a typical Go application. So what I do is there, I do a go run server.go, and it does its job essentially. Go run main.go, it will run the server. So first I'll start the server. It will start serving on port 8080, and then I'll go to the client folder and I'll start an HTTP server, and then I'll go and just demonstrate it. So I have this secret, so I'll click this button. It will send first the register call, and the server will respond that client public key is registered successfully. After that, it will get some like crypto material from the server. The public data is like public. The sensitive things like the AES key is encrypted with the server's public key, and also with the server's private key. And there is this signature material to like verify the entire transaction, so that nothing has been tampered in the meantime during exchange. And this N1 is a second level of protection against things like replay attacks. So this is the first message that comes from the server. It's like the empty state hello message. And let me go to the network tab to show you that no network I'm in the network tab, sorry. No interaction will happen when I click the decrypt button. So I'll click it, and it will, this is a secret message that comes from the server, and there's no network interaction. So if I encrypt and send this payload once more, this response will change, because it will do a second handshake, and the what we send from the client will be stored on the server this time. So when I encrypt and send, the server will return the server will store this data in itself, and it will return an encrypted version of the same data. Essentially, this is the data that it stored. So I can decrypt it, and you'll see that this is the same thing. So the cool thing is this payload is sent to the server in encrypted form as well. So when I see, where's my headers payload, you can see like this encrypted message to server. It is total like garbled text that a monster in the middle cannot decrypt, essentially. And here as well, it's all encrypted. Like anything that goes to the server is encrypted, even without a TLS or MTLS. And when I decrypt it, I see this one. So I can assume that I'm doing a UI. I want to change my password to I don't know, VMware secrets manager totally and equivocally rocks. Bang, 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 bang. Then I can encrypt it and send it to the server, and when I receive it, I'll get the decrypted data. So that's let me go back to the diagram here. This is this interaction that we have seen so far covers only this part. Right now, the server on behalf of VMware Secret Manager Safe is storing the data and returning it to the client. But in a real life scenario, the server will save the secret into VMware Secret Manager Safe, and for that, VMware Secret Manager Safe will require a bunch of policy entries to indicate that this server that is identified by this SPIFFE ID can write and read secrets for itself, but nobody else. So that gives a really great granularity. So the server can create secrets, but not for anybody else, because we have other workloads, even other servers of these kinds can use VMware Secrets Manager. And this kind of a policy will give a not network level, to be fair, but an application level tenant-wise isolation between these kinds of servers. Which is a good thing to have, especially when you don't want various data that various workloads have to be intermingled with each other. But having said that, that's all I have to share in this mini demo. Hope you liked it, and hope you keep your secrets secrets. Have a good day.